Okay, so let's look at these and draw the shear moment diagram for these two cantilevers. So we've done one with a constant load and no load. Now we've got a uniform load and a triangular load. Again, I'm going to shortcut the reactions a bit, and I'm sure if I gave you time, you could quickly figure out that the reaction here is WL, and that the moment is W naught L squared over 2. So with that, kind of as our background, let's see if we can construct the shear force and bending moment diagram. So don't forget that we start with the fact that the change in shear is the area under the load curve, and that the slope of the shear diagram is the value of the load. So what do we know about the shear? What's the shear here at the beginning? Well, the value is W naught L. It's up. Is that positive shear or negative shear? Positive. So we're going to start at a shear of W naught L. What's the shear at the free end? 0. Let's see if that's going to work for us. So it says that the change in shear from the left side to the right side should be the area of the curve from the left side to the right side. What's the area of the curve from the left side to the right side? It's a rectangle, so base times height, so it's W naught L. Don't forget, it's down, so it's negative. So that means we're starting at W naught L and we're subtracting W naught L. We get 0. And what's the shape of the curve? Well, it's equal to the load, and the load is constant, and it's negative. So here's a constant slope with a negative value. In fact, if we did the slope, it would be negative W naught. So there's our shear diagram. So where's the maximum shear? Here at the cantilever, the left-hand side. So now as we move to the moment, we know that the change in the moment is the area under the shear diagram, and that the slope of the moment diagram is equal to the value of the shear. So let's use these to help us construct the moment diagram. So looking at our beam, what's the moment, bending moment at the left edge? It's a negative bending moment, and we know the value is W naught L squared over 2. What's the bending moment at the right-hand side? Do we know that? It's free end. It's 0. So let's see if that works. So the change in moment between left and right should be the area of the curve between left and right. And what's the area of this curve? It's a triangle. 1/2 base times height. Right? 1/2 base L times height. W naught L is positive W naught L squared over 2. Oh, this was negative. So you add that together, you get 0. So that works. What about the slope? Well, it's equal to the shear. So what is the shear right here? It's W naught over L, and that's a positive shear, right? So that's a positive shear. And it decreases to a value of 0. What's 0 slope? It's horizontal, right? So that means our curve would fit something like that. So here again, our slope is 0 because that's the value. And here our slope, if you actually wanted to measure it, would be equal to W naught L. Everybody see that? So we don't really care. We know this is a quadratic curve. It's not really important what the shape is because where is the maximum moment? at the cantilever, and that's all we care about right now. All right, let's do this one. And this is where you'll start to see that where this technique might have some disadvantages. All right, so let's start with the reactions. Again, I know the reactions to this. This is going to be W naught L over 2 is the force, and the moment is going to be W naught L squared over 3. Let me think about that. I think that's right. Yeah, that's right. I'm sure if you had a minute to do it, well, you can see here that the concentrated equivalent would be the area of the curve, which is 1/2 base times height. That's how I get the W naught L over 2. And then the distance is 2/3 the distance, or 2L over 3. So you multiply it together, the 2's cancel, and that's how you get that. Now, in a normal problem with numbers, obviously you'd be responsible for making sure you get the right answers, but I want to focus right now on just these relationships. So we'll start here with the shear diagram. What's the shear at the left side? Positive or negative? Positive. You guys can play along if you like. It's W naught L over 2. What's the? Do you know the shear at the free end? 0. Now, according to our relationship, the change in shear between any 2 points is the area under the curve. What's the area under the curve from 0 to L? It's 1/2 base times height, which is negative W naught L over 2. So that brings us to 0. So that seems to work. Now, what's the shape of the curve? We start off with a slope of what? The load is 0. So there's our slope equals 0. And it increases to a large negative value. In this case, I missed my negative sign. Sorry, WL naught. So that should give you enough to hopefully draw the shape of the shear diagram. So since the loading diagram is linear, this is going to be quadratic. So now let's do the moment diagram. Our moment is W naught L squared over 3. What kind of bending moment is that? Positive or negative? Negative. So we're going to start off at negative W naught L squared over 3. What's the bending moment at the free end? 0. Now, if you want to check that, it says the area, the change in moment between the left and the right side should be the area of the shear diagram from the left to the right side. Now, probably most of you don't know the area under a parabolic section off the top of your heads. I just happen to know it. It's 2/3 base times height. So, would I expect you to know that off? No. But if you do look in your book, if you get into these situations, and you look in the back inside cover of your book, it will tell you both the area and the centroid of a parabolic section, and then its mate, what's called the parabolic spandrel. These two are common in shear force and bending moment diagrams. They both have a unique feature, is that one end of them has no slope, or it's flat. And our particular problem matches that, is that we start off with a 0 slope here. So our line of symmetry of our parabola is right there. So that works really well. So it would be 2/3 base times height. And then when you check that number, you'll find you get positive W naught L squared over 3. So it does bring you to 0. Now what about the shape? Well, according to this, the slope of the moment diagram is the shear. The shear starts off at a positive value and decreases to a 0. So the slope is 0 here. The slope value here would actually be equal to positive W naught L over 2. If I ever asked you that, then you'd be able to know that. So then you just kind of connect the dots. And there's our shear diagram. So went from linear to quadratic. This one's actually cubic. If you wrote an equation for this, it'd be a cubic equation. But again, where's the maximum moment? You can see it very, very easily on the graph. Any questions about these?